Hi, welcome back. In this video, I'll talk again about the bivariate normal distribution, and I have here our fun question. So here we want to look at the conditional expectation of x given a variable z, which consists of two random variables x plus y. So I think it's a fun question because usually if we have this variable z equals x plus y, we're asked what is the expectation of z given x. But in this case, we're interested in expectation of x given z, which I think is more tricky. So suppose we have two independent normal random variables, x and y. So x and y are normally distributed with known mean and variance, and let's define z equals x plus y. And now the question is, how do we compute the conditional expectation of x given z? So what is the expectation of the random variable x given z equals to some value? Well, since z equals x plus y, we want to find the expectation of x given x plus y equals some value z. Since x and z are correlated, because z equals x plus y, it depends on x, the pair x and z has a bivariate normal distribution, and the conditional expectation of x given z is a linear distribution of z because x and z are correlated. So if the expectation of x given z is a linear function of z, we know that this is a linear function. So now we just need to find a and b. And from theory, and you can look at another video which relates to this theory that I made. So from theory, we actually know a and b. So a equals covariance of x and z divided by the variance of z. And b equals mu x minus covariance of x and z divided by variance of z and times the mean of z. And all of these values are known because we know the distribution of x, so we know distribution of so we know the mean of x and the variance of x, so we know distribution of y, so we know mean of y and variance of y, and from that we can determine mean of z and the variance of z. And we can determine covariance of x and z, and then we can determine these a and b coefficients. So first we can use the independence of x and y, which means that covariance of x and y equals 0 to obtain the following. So covariance of x and z. So covariance of x and z, given z equals x plus y equals to covariance of x and x plus y. This should be y here. And that can be expanded to covariance of x and covariance of x and y. And we know from the independence of x and y that that is equal to 0. Therefore, this term here is just the variance of x, and this term here is 0. So we end up that covariance of x and z equals to variance of x. And variance of z, that's just the variance of x plus y. Well, we know the formula for that, and we know that covariance of x and y equals to 0. So we're just left with the variance of x and the variance of y. And we know that expectation of z equals to expectation of x plus y, and that just equals to mean of x plus mean of y. So this is mean of z equal to mean of x plus mean of y. So now we can use what we computed to substitute into our formula and derive the conditional expectation of x given z. So continuing with the calculations, we defined expectation of x given z as a linear function of z, and then we computed a to be this term here, and b to be this term here. And here we should have z, because this is a times z. Okay, so we can see that these two terms are the same. Therefore, we can actually take them outside of the brackets, which is what I do here, and we're left with z minus mu z in the brackets, and here we have plus mu x. And from what we computed, remember covariance of x and z actually just equals to variance of x. and variance of z equals to variance of x plus variance of y. So this is a variance of x plus variance of y, and this is our term in the brackets plus mu x. And we can easily interchange x and y if we're interested in the conditional expectation of y given z. So that would be the same. It would be variance of y divided by variance of z, which is variance of x plus variance of y, our term inside the brackets plus mu y. And also we want to check that the sum of the conditional expectations equals to z, because that's what it should be by the theory. So let's check that expectation of x given z plus expectation of y given z, does it equal to z? So this is our conditional expectation of x, and this is our conditional expectation of y. And we can see that here we have the same denominator. So then we can sum those two together. Well, that will be just equal to 1. Therefore, we're left with z minus mu z plus mu x plus mu y. But this term here, we know that equals mu z. Therefore, we have here z minus mu z plus mu z, which just equals z. So we checked our calculations for the conditional expectations of x and y given z are actually correct. So let's just do a simple example in R. So let's have random normal variables. So x is normally distributed with mean 2, variance 3 squared, y is normally distributed with mean 5, and the variance 5.5 squared. These are just some random parameters. And here I'm just going to plot a histogram of x. See here I generated 500 values for each variable x and y, and my z is just a summation of these vectors. So then I plot a histogram of x, color blue. I plot a histogram of y and histogram of z. Each of these vectors contain 500 values. So here are our histograms. This is x, this is y, and this is z, which equals x plus y. So now we want to see how x depends on z. And you can see somewhere this is the mean here. It should be around 3. It doesn't have to be exactly 3 because this is a sample. Mean of y should be 5.5, but we'll check that. So let's check mean and variance of our variables. Yeah, so I just made a data frame and I decided to convert each variable to an integer because I actually want values to repeat so that for a given z we could have multiple values of x, so we can compute the mean of x in distribution. I just named the columns of my data frame, and then I just compute the means of each column. So this is my output here. This is the mean of x, this is the mean of y, and this is the mean of z. So yeah, from the sample we got the mean of x lower than 3, but well, that's just random. So the mean of x is 1.5, mean of y is 4.8, and remember we said that we said that mu z should equal to mu x plus mu y. So we're just checking. Here we're adding mean of x and mean of y, and we get 6.382, which equals to the mean of z that we computed here, so therefore it's correct. We check that mean of x plus mean of y equals mean of z. And here we're just calculating the values for each column. And remember, we also determined that in theory, sigma z squared should equal to sigma x squared plus sigma y squared. And that's what we want to check. So I'm adding the sample variance of x and sample variance of y, and I obtain a number which is very close to the sample variance of z. So this is a 32.95, and here we have 32.36, so that's pretty close. And now we're interested in the conditional mean. So that's our formula. Remember the linear formula for the conditional mean. Can we actually get these results with sample data? So here I'm computing the mean of x, and here I want to compute the conditional mean of x given that z equals to 3. And here I compute mean of y. Remember, this is the sample mean. In our data, we have 500 points. And here I'm computing the conditional mean of y given that z equal to 3. And that's why I converted the values to integers, because for z equals 3, we want to have multiple values of x and y. And we want to check whether the sum of the conditional means equals z, because remember our theory said that the sum of the conditional expectations given z should give us z. So let's check whether that's true. So mean of x from before, we already know it's the sample mean is 1.5. But look, the conditional mean of x when z equals to 3 is much lower than 1.5. And same for y. The sample mean of y is 4.8, but the conditional mean here is much lower. It's 2.1. And when we sum 0.875 plus 2.125, so we're summing the conditional means, we get 3. So we get our z. And therefore, we're getting the results consistent with the theory. Here I'm just trying to compute the conditional mean of x given z for each value of z, because previously I just did it for z equal to 3, but z is a vector which can hold different values. So here we obtain our possible unique z, like the unique values that z holds in our sample. And here, for each unique z, this is a loop, for each unique z, I compute the conditional mean of x for that value of z. And then we want to check with our formula, because I remember our formula is that the expectation of x given z equals covariance of x and z divided by sigma z squared times z minus mu z plus mu x. So we want to check if that formula works for our sample. So we need to compute the covariance of x and z. Here, then we perform this formula. So this is our covariance of x and z. This is our sigma z squared. This is our vector of unique z minus mu z and plus mu x. So here we obtain a vector. So for each z, we obtain the conditional expectation of x for that value of z. And now we can plot our unique z and the actual conditional mean. And then we can also plot the unique z and the theoretical conditional expectation and check whether the sample and the theoretical values are close. So we can see here the line is our theoretical line for the conditional expectation, where I said previously what the A and B are, and the points that you see here are the sample conditional means. So we can see that the points are pretty close around the theoretical line. So this shows that this relationship is well described by the formula that we obtained.